Yes, in this video we will see how to apply the calculated loads on ground tank. Okay, so if I open my ETABS model, so this is on ground tank. We already have this model with us. So size of the tank is 10 by 8 by 5 meters. Grade of concrete M30, steel Fe 500. So this wall thickness is 350 mm, 350 mm. Whereas your base slab thickness is 500 mm. Okay, so first we will see how to apply the loads. So over the past 2-3 sessions we calculated hydrodynamic pressure on base slab and hydrodynamic pressure on walls. We will be using the same calculations. Okay, first we will see how to apply EQX and EQ minus X loads. Okay, so EQ X and Y means if you open our ETABS model, so if you go to plan view of the tank, so this wall will be chosen for EQ plus X, whereas this wall will be chosen for EQ minus X. Okay. So our final hydrodynamic load distribution was like this. So at the bottom it is 17.80 kilonewton per meter square. At the top it is 4.95 kilonewton per meter square. So Z equals 5 meter height of the tank. So here at the bottom Z equals 0. Okay. The equation is simple. Ax plus by plus cz plus d equals 0. So here the pressure distribution is along z direction. So x value is 0, y value is 0. So cz, sorry, this is not 0, 0 here. So it is ax plus by plus cz plus d equals any pressure. So cz plus d equals, so in our case it is hydrodynamic water pressure. Hydrodynamic water pressure. Okay. So first condition is when Z equals 0, so your hydrodynamic pressure will be 17.80 kilonewton per meter square. So when Z equals 5 meter, so your pressure, hydrodynamic pressure is 4.95 kilonewton per meter square. So if you substitute these two conditions in the above equation, so C, first Z value is 0 plus D equals 17.80. So first we will check the direction of local axis. We go to our ETABS model. So object assignment. In case of shell assignment, we will turn on the local axis. Okay, so for these two walls, shorter walls, so here it is local axis is inward, and for this wall local axis is inwards. Okay, so for the walls along grids A and B, so orientation of local axis is inward. So I am applying the pressure in opposite direction. Okay, so assumed local axis 3 was inside, I am applying the pressure in opposite side. So in that case, so here it is minus 17.80. So C into 5 plus D equals, so this is minus 4.95. So this is equation number 1. This is equation number 2. Okay. So here from equation 1 we will get D value directly. So D equals minus 17.80. Okay. So if you substitute D in equation number 2, so that is equation number 2 is 5C minus D is 17.80 equals minus 4.95. So 5C equals minus 4.95, which is plus 17.80. Okay, so C will be minus 4.95 plus 17.80. So it is 12.85. 12.85 divided by 5. So which is 12.85 divided by 5. So which is 2.57. Okay. So 2.57. So for EQ X and EQ minus X, so your C value is 2.57, whereas your D value it is minus 17.80. So you please remember these two. Okay. So we will see the load application in ETABS. So if you select your, so I will be applying loads on these two walls. Okay, that is wall along elevation B and wall along elevation A. So wall along elevation B is chosen for EQ plus X, whereas wall along grid elevation A, which is chosen for EQ minus X. So you go to elevation. So you go to wall elevation along B, which means this wall. So apply. Okay. You select this wall. Okay. You go to 3D view to confirm the wall. Yes, we have corrected the EQ plus X. Okay. So you go to, see here, in the last video we already created the load patterns. So EQ X, EQ minus X, EQ Y, EQ minus Y. Okay. So you go to assign shell loads non-uniform. Okay, it is in EQX. Okay, it is along local 3. So A is 0, B is 0. So here we need to use C and D values. So C value is 2.57 here, 2.57, and here it is D value is minus 17.80. Minus 17.80. Okay, so you click on apply. Okay, so you go to display undeformed shape. So you go to elevation. So elevation along B, click on apply. OK. So if you choose any one of the element and you go to loads here, see here. So on this shorter wall, we have applied our hydrodynamic pressures. Okay. So next we will take EQ minus 6. So go to plan, top of tank for EQ minus 6, which wall has to be selected for EQ minus 6, the wall along elevation A. So you go to elevation, so you choose elevation A, you select all the elements present in this view. So you go to assign shell loads non-uniform. See here it is minus EQ minus 6, local 3, same C and D values 2.57 minus 17.8. Okay, so you click on apply. Okay, so you go to display undeformed shape. See here. So this is the load what we assigned on our shorter walls. Okay, so EQ plus X is completed, EQ minus X is completed. So next we will go for EQ plus Y and minus Y. So EQ plus Y and minus Y. Okay, so you go to plan. So for EQ plus Y, this wall has to be selected, the wall which is present along elevation, grid elevation 2, and for EQ minus Y, the wall which is present along grid elevation 1. Okay, first we will calculate the C and D. So next it is we will calculate C and D values for EQ Y and EQ minus Y. The final pressure distribution, hydrodynamic pressure distribution on wall. So we calculated like this. Okay, so here Z is 0, wall elevation. So here height of the wall is 5 meter. So at the top it is 4.73. At the bottom it is 17. At the bottom it is 17.48. Okay. The equation is AX plus BY plus CZ plus D equals pressure. So again here X and Y are 0 because my pressure distribution is along Z direction. So equation will be CZ plus D equals P. So first we will write the conditions. So first condition is when Z equals 0, so your P is 17. Again it is minus 17.48 because my local axis 3 is inwards. So second condition is when Z equals 5, so P equals minus 4.73. We will substitute these two conditions in this equation. Okay, so C into 0 plus D equals minus 17.48. So here we will get D value directly because this is 0. So D is minus 17.48. Okay. So next, C into 5 plus D equals minus 4.73. Okay. So C into 5, here D value is minus 17.48 equals minus 4.73. Okay. So 5C equals, so it is minus 4.73 plus 17.48. So minus 4.73 plus 17.48. So which is 12.75. So 5C equals 12.7. How much it is? 12.75. So C equals 12.75 divided by 5. 12.75 divided by 5 equals 2.55. 2.55. So here C is 2.55. D equals minus 17.48. So these are the C and D values for EQY and EQ minus Y. Okay, so we will see the load application. So you go to ETABS. So for EQ plus Y, you have to select this wall. So go to elevation along 2. So you select all the elements. You go to assign shell loads non-uniform. So in this case it is EQ plus Y local 3. So C is 2.55. 2.55. D is minus 17.48. Minus 17.48. So you click on apply. OK. So display undeformed shape. Again you go to next wall. So for EQ minus Y, this wall has to be selected. So you go to elevation along grid 1. Okay, you select all the elements. So you go to assign shell loads non-uniform. So EQ, now it is EQ minus Y local 3. So C and D remain same, 2.55 minus 17.48. So you click on apply. OK. So you go to display undeformed shape. Okay. So we completed the first part, that is hydrodynamic load application. Hydrodynamic load application on walls. Hydrodynamic load application on our walls. We completed load application on short walls and long walls. So for short walls it is EQ plus X and EQ minus X. For long walls it is EQ plus Y and EQ minus Y. Okay. So once it is completed, we will apply hydrostatic loads. Hydrostatic loads, that is water loads. Water loads. The tank is filled with water. So we will see how to apply the loads. Okay. So if you take elevation of the wall, here at the bottom Z is 0, at the top Z equals 5. Okay. So the water distribution is triangular in nature. So at the top it is 0 kilonewton per meter square. At the bottom it is 50 kilonewton per meter square. It is nothing but height of the wall multiplied by density of water. Okay. So for this case it is AX plus BY plus CZ plus D equals pressure. So if you remember, my local axis 3 was inside. So AX 0, BY 0. So here it is CZ plus D equals P. So first condition is when Z equals 0, my pressure is minus 50 kilonewton per meter square. So second condition is when Z equals 0, sorry, not 0. So when Z equals 5, my pressure is 0. Okay. So we will calculate the C and D values. So C into Z. So Z is 0 plus D equals P is minus 50. So here C 0. So we will get D value directly. So D is minus 50. D is minus 50. Okay. So next is to calculate the C value. So C into 5 minus 50 equals 0. Okay. So here, so C will get it as 10. Okay. See, for hydrostatic loads, so your C value is 10 and D value is minus 50. Okay. For this hydrostatic loads, you select all the walls. So you go to elevation. So you select first wall, second wall, next your long walls, wall number 3 and wall number 4. You have to select complete your walls. So go to assign shell loads non-uniform. So now it should be under water pressure. So local 3. So your C value is 10. And D value is minus 50. So you click on apply. Okay. So you go to display undeformed shape. You go to any elevation. So if you want to check shorter wall, you go to elevation B. If you click on any element, see here one is EQX, your hydrodynamic pressure, and this is hydrostatic pressure, which is water pressure. Both should be along non-uniform. Okay, so once it is completed, next we will assign hydrostatic loads on our base slab. Hydrostatic loads on our base slab. Okay, so how to assign this? At the bottom, your water pressure is 50 kilonewton per meter square. On the base slab, it is in uniform distribution. Okay, so it is along gravity direction. So you go to your ETABS model. So you select your base slab. So you select your base slabs. See here, 1 shells, 4 edges selected. So you go to assign shell loads, uniform. So it should be under water pressure. So it is along gravity direction. So it is 50. Click on apply. Okay. So if you check your base slab, see here. Now it has only water pressure. Uniform water pressure. Okay. So next we will, in the next case, we will assign hydrodynamic water pressure on base slab. So we will, so first it is EQX and EQ minus X, EQY and EQ minus Y. Next we completed this third step, hydrodynamic load application on walls. Next hydrostatic. Next this is on our walls, hydrostatic loads on walls. So this is hydrostatic loads on base slab. So next we will assign, next step would be application of hydrodynamic water pressure on base slab. Hydrodynamic water pressure on base slab. I think you remember the pressure distribution in my previous classes. So if you go to your ETABS model, so if you check your base, see here. So here X is 0. So here X is 5 and here X is 10. So when your load EQX is in this direction, so this is the center line of your wall or tank. So your pressure distribution will be like this. Your pressure distribution will be like this. At the center it is 0. At this end it is 12.71. Okay. If you see here, pressure variation is along X direction. Now it is not in Y and Z. The pressure distribution is along X direction and it is along gravity direction. And it is along gravity direction. So pressure varies along x-axis. The pressures are applied along gravity directions. Okay. So here first condition is when x equals 5. X equals 5. So your pressure is 0. When here it is when x equals 10. When x equals 10. So your pressure is 12.71. Okay, we will calculate the constants. See here. So here ax plus by plus cz plus d equals pressure. So here y is 0, z is 0 because my pressure varies along x-axis. So here equation is ax plus d equals pressure or hydrodynamic pressure. So first condition is when x equals 5. So a into 5 plus d. When x equals 5, p is 0. So next is when x equals 10 meter. So d equals 12.71. Okay. So for these two equations, so a value is 2.542 and d it is minus 12.71. So a and d values are like this. So this is for EQX. What it is? Hydrodynamic water pressure on our base slab. Okay. So to apply this load EQ plus X, see here, you first select your base slab. Okay. So you go to assign shell loads. Okay. It is non-uniform. Non-uniform and EQX. Okay, it is along gravity direction. So here A is 2.542, B0, C0, D is minus 12.71. So C0, D is minus 12.71. Okay, so you click on apply. Okay. So if you see here, you have the hydrostatic pressure 50 and EQX. So in addition to this, you have vertical acceleration. I think it is constant value of 9 kilonewton per meter square. 9 kilonewton per meter square. So you go to, so it is uniform. This pressure is uniformly varies. So you go to base slab. You select your base slab. Go to assign shell loads uniform along EQX. So load is 9. It is along gravity. You click on apply. Okay. So now you check along EQX. You have hydrodynamic pressure and your pressures due to vertical acceleration. Okay. So this is for EQX. Similarly, EQ minus X. So similarly, EQ minus X. So EQ minus X, it is opposite. So here it is X value is 0. Okay. So at the center it is X 5 meter, X is 10 meter because your length of the wall is 10 meter here. So if this is your center of the tank, the pressure distribution for EQ for EQ minus X earthquake load, your pressure distribution is like this. Your pressure distribution is like this. So first is when X equals to 0. So here pressure is 12.71. So your pressure is 12.71. So here when Z equals, when it is not Z, it is X. So when X is 0, your pressure is 12.71. So here when X is 5 meter, your pressure is 0 here. Okay. Again, for this case, we will calculate A and D values. So this is for EQ plus X. So similarly, we will calculate for EQ minus X. So this is for EQ plus X. So for EQ minus X. So AX plus D equals pressure A into 0 plus D equals, so when X is 0, your pressure is 12.71. So when X is 5, so your pressure is 0. So by these two equations, solving equation 1 and 2, so your A is minus 2.542 and your D is 12.71. So these are hydrodynamic loads in addition to that vertical acceleration. So it is constant 9 kilonewton per meter square. So you select your base slab, go to assign shell loads non-uniform. So now it is in EQ minus X along gravity direction. A is minus 2.542 minus 2.542. B and C are 0. Here it is 12.71. 12.7. B and C are 0. So you click on apply. Okay. So this it is completed. Now this 9 kilonewton per meter square. So you select this, go to assign shell loads. Now it is uniform under EQ minus X. So this value is 9. Direction is gravity. You click on apply. Okay. So see here EQ plus X, and this is EQ minus X, and this is hydrostatic water pressure. So similarly now it is required to calculate for EQ plus Y and EQ minus Y. EQ plus Y and minus Y. So for EQ plus Y, see here, EQ plus Y. So EQ plus Y, it is along this direction. This is EQ plus Y. At this point, Y is 0. At this point, Y equals 4. At this location, Y equals 8. Okay. If you consider center line of the tank, okay. So pressure variation would be like this. So half of the tank will lift up. Okay. So it is 11.91. So here it is 0. So conditions are when Y equals 4, your pressure is 0. Here the pressure varies along Y direction. So here it is when Y equals 8 meter. So your pressure is 11.91. Okay. So we will calculate B and D. So first calculation is for EQ plus Y. So equation is AX plus BY plus CZ plus D equals your hydrodynamic pressure. So here pressure varies along Y direction. So because of which X0, Z0. So equation is BY plus D equals pressure. So according to the conditions, so when Y equals 4 meter, pressure is 0. So next when Y equals 8 meter, pressure is 11.91. So solving 1 and 2. You will get B equals 2.975. D equals minus 11.91. So these are the B and D values. So similarly for EQ minus Y, so your B value is minus 2.9775 and your D value is 11.91. Okay. So in addition to that, you have a uniform pressure of 9 kilonewton per meter square. In addition to that, you have 9 kilonewton per meter square. So you go to ETABS model, you select your base slab, you go to assign shell loads. First, it is non-uniform. So EQ Y. So for EQ Y, A is 0. So B is 2.9775. C 0. D is minus 11.91. So you click on apply. Next you select your base slab. You go to EQ minus Y. EQ minus Y. So A 0. So B is, it is minus 2.9775 and C is 0. D is 11.91. So you click on apply. Okay. So you select your base slab. Go to assign shell loads. Now it is uniform. EQ Y 9 gravity direction. Click on apply. Again you select your base slab. EQ minus Y 9 gravity. Click on apply. Okay. See here on your base slab, this much load has to be applied. So if you see carefully, EQ minus X, EQ plus X, EQ minus Y, EQ plus Y. So along each direction you have hydrodynamic pressure, vertical acceleration, hydrodynamic pressure, vertical acceleration, hydrodynamic, vertical acceleration, hydrodynamic pressure, pressure due to vertical acceleration. So these are hydrodynamic pressure, whereas this is hydrostatic pressure. Okay, so this is the load application. So carefully assign these loads to your model. Next we shall see load combinations. Next step is to create load combinations. Again we will be referring IS 3370 part 2 2021. So that is table 1. So IS 3370 part 2. Yes, this is the table we will be using for creating load combinations. Again you have two cases. One is limit state of collapse. Another one is limit state of serviceability. So here DL, in case of load cases, DL stands for dead load. IL stands for imposed load or live load. This is EP stands for earth pressure. This FL stands for fluid pressure, water pressure, and these are wind load and earthquake load. So anyway, we will not be using this earth pressure here and live load here. Okay. So our tank is on ground tank. No soil pressure from outside and we have not modeled any top slab, so there is no live load. So these two are not required for us. Okay, so from this table, for limit state of, I have made a table like this. See here. So these are the load combinations. So under limit state of collapse, you have 13 cases. You have 13 combinations. And in case of limit state of serviceability, you have 5. Okay. So first is 1.5 dl plus 1.5 water pressure. Next is 1.2 dl plus 1.2 water pressure plus 1.4 EQX. Next, same for EQ minus X. Next is EQY. Same for EQ minus Y. The combination is same, but you have 4 directions. So one is EQ plus X, EQ minus X, next EQ Y and EQ minus Y. Okay. So you have to create 13 combinations in case of limit state of collapse. In case of limit state of serviceability, you have to create 5 load combinations. Okay, so you take a screenshot of this and you start creating your load combinations. So be careful while creating the load combinations, because you have to use the correct factor and correct direction. So already you know how to create the load combinations. So today's assignment is you create 13 limit state of collapse combinations and 5 limit state of serviceability combinations. Okay, so with this I will be end this video. So next we will see, once we create the load combinations, next we will see the analysis part. So you try to create these combinations. So I will demonstrate it for one combination. So first we will create this combination 1.5 dead load plus 1.5 water pressure. So to create this, you go to your ETABS model, you go to define load combinations. So if you have any existing load combinations, you just delete it. You go to add new combo. So first combination name is 1.5 dl plus 1.5 water pressure. So you go to linear add 1.5, add water pressure 1.5. You click on OK. See here. So this is the combination we have created, 1.5 dl plus 1.5 water pressure. So similarly we will create this limit state of serviceability dl plus water pressure. So here factor is 1. So add new combo. So this combination is dl plus water pressure. So combination type linear add. So by default you have dead with scale factor 1. You go to add. So water pressure with scale factor 1. So you click on OK. So like this you have to create all other combinations. So once you create all the combinations, you will get a list of created combinations. You just click on OK. So now you are ready for analysis.